everyone, this lecture is powered by Study Studio channel and presented by me, Saiankit. This is about me. I stay in Hyderabad and I am a study enthusiast who is eagerly waiting to be an undergrad. Welcome to lecture number 3 of Modern Physics. If you haven't watched the previous lectures, please watch them for a brief introduction of today's lecture. Coming to today's class plan, we will be discussing the experiments of Hertz and Lenard, their relation with photoelectric effect, the laws of photoelectric effect, and an important question answered at the end. A detailed problem-solving session on this topic is awaiting in the upcoming lectures. So, Heinrich Rudolf Hertz was a German physicist whose name was tagged as a unit for cycles per second, Hertz, as an honor. So this thing right up here is the experimental setup of Heinrich Hertz, who first conclusively proved the existence of electromagnetic waves through his experiment. And let us know what is it. Let me explain to you the setup and prerequisite directions taken by Hertz in setting up this thing, okay? The coil right here is a high tension coil having high L value. L refers to the self-inductance of the coil here. It's assumed that you have read about this during the induction part of the electromagnetism chapter. And the switch right here is basically turned on and off just immediately so that the time lag between them is very less. I mean very less. So why is it done so? Why is the L value maintained high and why is the time lag taken? If we see this formula for induced EMF, and if you observe here, E refers to the induced EMF, L refers to the self-inductance of the coil, and di by dt refers to the rate of change of current through the coil. And if you observe in the experiment, the L value is maintained high and also the time is very less. I mean the change in time, though dt, and since L is directly proportional to E and dt is inversely proportional to E, there is a combined effect applied and a high potential is created near the coil. These balls right here are large metal balls and these small things are the small metal balls kept in the circuit. And due to a large potential difference created near the coil, the large metal balls charge up, and when these charge comes in contact with this small metal balls, a spark is observed here. So one more thing to note is that the charge following has such huge voltage that is exceeds the breakdown voltage of A to create a spark, and this is due to the combined effect of those we discussed earlier. And when he saw the sparks in this small gap, he placed a small detector loop somewhere near the main loop, and he saw high voltage sparks across the detector loop also. He concluded that some waves are generated which are later known as electromagnetic waves at that initial gap, and they travel the energy to the detector loop. Hertz did not realize the practical importance of his experiments. He said that it's of no use whatsoever. This is just an experiment that proves Maxwell was right. We just have these mysterious waves that we cannot see with the naked eye, but they are there. Let's see what Maxwell said in upcoming classes later, but in brief, what Maxwell said was that electric and magnetic fields move perpendicular to each other and electromagnetic waves are generated, and he found out that electromagnetic radiation has the same speed of light, so light is also an electromagnetic wave. This is what, in brief, what Maxwell said. So now let's discuss the Lenard's experimental study of photoelectric effect. This is an evacuated glass tube. As in the cathode ray experiment, it has two electrodes connected to a battery, and you have a rheostat for varying the voltage in the circuit. You have the commutator here for reverting the electrodes, and we have an opening here for the entry of light. Also, we have attached a quartz window for allowing only particular type of light or particular frequency of light. So when the key is open, it means that the circuit is not completed, right? And no current is flowing through the circuit. And when light is incident on this cathode, we can perceive small current in the microammeter right here. And current is measured even though the voltage is zero here. So when the photons of the light hit this photosensitive plate, that is a plate which is sensitive to photons, then some work function is provided by the photons and electrons of the metal are released into the evacuated space. So these electrons from now are to be called as the photoelectrons, the electrons which are released due to the photon incidence. If the energy of the incident photons is more than the work function of the metal, then the photoelectrons move a bit in this evacuated space and constitute something which we call as space charge. The electrons stay in the evacuated glass tube in this evacuated space and they form the space charge kind of a thing. And if the energy is only sufficient for work function, only electrons are released into this evacuated space, and when space charge is there, right in the evacuated space, then the circuit finishes and the ammeter reads current. Now Lenard closed the switch and observed the current when the anode was given a positive terminal with respect to cathode. The electrons in the evacuated space, that is the space charge, are attracted by this anode because electrons are negative charges and anode is positive with respect to cathode. So electrons are attracted towards anode and photoelectric current is produced and perceived even better than the earlier case. Now what Lenard did was he increased the voltage of the anode. That is, he made anode more and more positive using the rheostat we incorporated in the circuit earlier. The effect of space charge reduced, it means there are no stagnant electrons left in the evacuated space, and all the electrons emitted by the photosensitive plate are attracted by the anode and the circuit is completed. And after a while, the change in current is not perceived. No doubt there was a current, but no difference in rise or fall of current is observed. So the current becomes constant even though the voltage is increased, and this current is known as saturation photocurrent. When anode is given negative terminal with respect to cathode, this is made possible by this thing called commutator. Then the electrons emitted by the photosensitive plate will get repelled by the plate and electrons go back to the cathode. So gradually the photoelectric current decreases, and at some point of negative anode potential, the current becomes zero also. That minimum negative potential given to the collector electrode, that is anode, with respect to the emitter electrode, that is cathode, for which the photoelectric current or photocurrent becomes zero, is referred to as stopping potential. So why did I mention collector electrode and emitter electrode is because we can't mention anode and cathode because we are reverting the signs of the electrodes. So collector electrode is that thing which collects the electrons or attracts the electrons, and emitter electrode is the photosensitive electrode. The work done by stopping potential is equal to the work done by kinetic energy. So what do you understand by this simple equation? It means that the stopping potential does that much work which could even stop the most energetic photoelectron to reach the anode. Okay, that is, at this potential even the most energetic electron fail to reach the anode. This is what we discussed, and the work done by potential is given by EV, so minus E for the negative charge and minus V naught for the negative potential. We denote the stopping potential with the sign V naught is equal to half m Vmax square, where Vmax is the maximum velocity of the most energetic electron, so EV naught equal to half m Vmax square. You might not encounter direct problems on this topic or formula, but these formulas are incorporated in large questions which we'll be discussing in upcoming classes. Here in this graph, let us know what is plotted. On the x-axis is anode potential difference, and on the y-axis is the photoelectric current measured on the microammeter. In this graph, we can see all the observations made by Lenard. The saturation photocurrent, which is constant, and the negative anode PD, which is V naught here, is the stopping potential. These are what are described by the Lenard's observations clearly. Now let's discuss the effect of various factors on photoelectric effect. Effect of intensity of light. When anode is positive with respect to cathode and its potential difference is kept constant, there is some saturation photocurrent after some time, right? So let's take I naught to be saturation photocurrent and I to be intensity of the incident light on this graph here, and we can observe that intensity of incident light is directly proportional to the saturation photocurrent. When the intensity of the incident light is more, then the saturation or constant photocurrent increases linearly, that is directly. There is no threshold intensity like a kind of thing for photoelectric effect to occur, but a bright light yields more electrons than a dim one. A very little intensity is also enough to emit electrons, but there's another clause which we'll be discussing later about frequency. Effect of intensity of potential difference applied or the voltage. As discussed earlier, when the anode is made positive, after some time saturation current is reached, and after that there is no effect on potential difference. So when anode is positive, there is no effect on PD after saturation state. Right, we can observe here. The potential difference is increasing, but the saturation photocurrent is constant. But initially, when anode potential difference increases positively, there's a little increase kind of a thing in current, and later it becomes constant. So from the given graph, we can understand that since saturation current depends on intensity of light, saturation current varies with respect to intensity. But at V naught or the stopping potential, the electron is just prevented from reaching the anode, and it has nothing to do with the intensity of light. Hence, the V naught or stopping potential is independent of the intensity of the incident light. Effect of frequency of incident radiation. For a given same intensity of light, the rate of photoelectric emission is constant. That is, the saturation current is not at all related to the frequency of incident radiation. But no doubt there must be some threshold frequency for current to generate, which I'll be discussing about soon. But when frequency increases, kinetic energy increases, and when kinetic energy increases, then stopping potential also increases. I mean, negatively for sure. So this is what we can observe in this graph. When nu2 is greater than nu1, then v02 is greater than v1. Threshold frequency, a characteristic property of matter, here metal plate, to not allow the electrons to get removed from the plate is defined as threshold frequency. It is denoted by the symbol nu naught, where nu is the symbol for frequency and nu naught refers to some constant frequency or threshold frequency. It means that it is the minimum frequency of incident light for which the electrons just come out of the plate with a no or zero velocity. So electrons are emitted out of the plate only when the frequency is more than the threshold frequency. A similar quantity to threshold frequency is threshold wavelength. And electrons are emitted out of the plate only when the wavelength is less than the threshold wavelength. You'll discuss more about this threshold frequency and its application in Einstein's photoelectric concept, which we'll be discussing in next class. An important note to be noted is that in this chapter we consider the number of photoelectrons emitted equal to the number of photons incident on the metal surface. This is an important note to be followed while solving the problems. But if and only if stated about quantum efficiency, then we'll disapply this note and follow the quantum efficiency concept. So what is quantum efficiency concept? So quantum efficiency. When quantum efficiency is mentioned, it implies that not all photons incident give rise to electrons. How to find that number of photoelectrons emitted when the number of photons incident are known and the quantum efficiency of the circuit is known? So the quantum efficiency or efficiency in general is number of photoelectrons emitted upon the number of photons incident. This quantum efficiency is always less than 100% unless and until number of photoelectrons emitted is equal to number of photons incident. Based on these experiments and conclusion calculations, there were some laws devised known as laws of photoelectric effect, which are very important to understand but generally neglected in the coaching. These laws help us to get answer the question which is to be discussed at the end of this lecture. Law number 1. The number of photoelectrons emitted per second is directly proportional to the intensity of incident radiation, assuming 100% efficiency. So this assuming 100% efficiency clause is very much required, and I'll be explaining you how we came across this law in the next slide. According to quantification of charge, we assume that Q equal to NE, right? So here N is the number of electrons and I is NE by T. So I is proportional to NE. That is, saturation photocurrent is proportional to the number of photoelectrons emitted, right? And as we assume 100% efficiency, so NE is directly proportional to NP, so I is directly proportional to NP, where NP is the number of photons incident. And since intensity of incident light is proportional to saturation photocurrent, as we have seen in effect of intensity of incident light in the observations of Lenard, so I is proportional to I, that means the intensity is proportional to saturation photocurrent. So therefore intensity of incident light is proportional to number of photons or directly proportional to number of electrons. So the number of photoelectrons emitted per second, or you can also take by the NE by T concept by taking this NE by T or varying the time also, right? Emitted per second is directly proportional to the intensity of the incident radiation. Law number 2. The photoelectrons are emitted with a range of kinetic energies from 0 to a maximum, which increases as the frequency of radiation increases and independent of intensity of radiation. So the maximum kinetic energy is the work produced by stopping potential, right? So here the photoelectrons are emitted with a range of kinetic energy from 0 to a maximum. So this maximum is the effect of stopping potential, which increases as frequency of radiation increases, as we have seen that stopping potential increases as frequency of radiation increases, and stopping potential is independent of intensity of radiation. This is what is said in law number 2. Law number 3. For a given metal, there is certain minimum frequency of radiation called threshold frequency, below which no emission occurs, irrespective of the intensity of light. Law number 4. There is no time lag between incident energy and photoelectron emission. Due to some explicit calculations, this is an well-known accepted fact that there is no time lag between incident energy and photoelectron emission. It just takes some microseconds for the process to occur. The question which I was talking in the start is about to come. Did wave theory explain the photoelectric effect? So you might think this simple question, and I was saying that it's a very typical or a very important question. So you'll know why is it important also. First, let's discuss what is the answer that came to this question. The answer to the question was no. A simple no is the answer, that wave theory did not explain the photoelectric effect. So what's a big deal in that photoelectric effect was not explained by wave theory? Is it so important? Yes, it's indeed important. We'll know why is it important too. Why is it important to study about this question? This one question ruled out the existence of wave theory and particle theory of light in the history of light conflicts. And how come this question ruled out? We will discuss it now, and you might be fascinated to know how. In accordance with wave theory, the energy carried by a beam is measured in terms of intensity. And greater intensity implies greater amplitude, and greater amplitude implies greater energy. When a beam of light is incident on the metal, the energy carried by the beam will be equally distributed among the electrons, and these electrons, on accepting energy, will be ejected from the metal surface. Fine. When the waves of light of higher intensity fall on the metal surface, more energy will be imparted to the electrons, thus the kinetic energy of the emitted or ejected electrons increases. So this is a contradiction to law number 2. Why? Because the maximum kinetic energy of the emitted electron is independent of the intensity of incident beam, right? So the maximum kinetic energy is nothing but about the stopping potential thing. It is independent of the intensity of incident beam. So wave theory failed here. In accordance with wave theory, no matter of frequency of light, electrons should be ejected. Only requirement is the intensity of light, right? The concept of threshold frequency shouldn't exist in that case of wave theory. But experiments show that threshold frequency exists according to the laws devised for photoelectric effect. So wave theory again failed here, and this is a contradiction to law number 3. In accordance with the wave theory, the energy possessed by the beam of light is smoothly and uniformly distributed across its advancing wavefront. So what are wavefronts and all, you will be discussing in wave optics theory if you haven't discussed until now. The energy carried by the beam is not received by just one electron. Instead, the energy is equally distributed among all the electrons that fall in the part of the surface of the metal which is illuminated. Thus, all the electrons receive this amount of energy which is distributed among themselves, and thus each electron receives only an insignificant amount of energy. So, the electrons should take a finite amount of time to escape the surface of metal. So, this process of advancing wavefront energy theory takes some time to complete. So calculations show that this finite time is somewhere near hours. So wave theory again failed here. This is a contradiction to law number 4 which we discussed earlier. When the particle theory of light and wave theory of light were in a melancholy, a new theory came to their rescue, the quantum theory, which devised all the solutions to the problems of the conflict, which we'll be discussing in later classes. Up next in the class, we'll be discussing the most famous Nobel Award-winning theory, the Einstein's photoelectric theory, which forms a major chunk and reason to solve a hell lot of questions on photoelectric effects. This theory paves the way for our problem-solving session next. But in next class, we'll be discussing some basic and intermediate level problems and discuss some related previous year problems also. You can find us on social media through our Facebook page, Instagram handle, and you can also mail us your queries at studystudio.saiankit@gmail.com. Please like, share, and subscribe to Study Studio for more videos to boost your JEE or Bitsat score. Don't forget to turn on the bell icon for not missing your favorite lectures here.